Okay, let's continue. And let's continue by mentioning another result concerning the strange modes in Wolf-Rayet stars, because we have also done non-radial, non-adiabatic computations for a Wolf-Rayet star. So the model we are considering is a helium 0H main sequence star with 0 hydrogen content, 0.98 in mass helium, so it's almost a pure helium star with 2%. That means solar metallicity. The star has 16 solar mass. It's one of these objects which we have considered before. But now we are applying non-radial perturbations to our model. It's a single stellar model, and we consider the spectrum of eigenfrequencies as a function of harmonic degree. So the highest harmonic degrees we have here is 300, and it goes to 0, meaning radial perturbations. In the left diagram, we have the real value of the eigenfrequency. In the right part, in the right panel, we have the imaginary part of the eigenfrequency. Now what we observe here, it's also a very complicated and bewildering diagram which we obtain here. For simplicity, let's start at very high values of the harmonic degree, 300. Well, what we observed once we look at the high harmonic degree is a spectrum like we expect for an ordinary acoustic resonator. It has a fundamental mode here, or mode which we call a fundamental mode. It's of course a fundamental P mode. And then we have a sequence of more or less equally spaced eigenfrequencies, so the spectrum looks like that of a normal organ pipe. All these modes here are damped, and this damping rate here amounts up to, say, 0.5. This bunch of lines corresponds to the damping rate, the intrinsic damping rate of all these modes. Now, if we decrease the harmonic degree, we observe that these modes merge and form an almost complex conjugate pair. This happens here, 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 and so on. It obviously is not restricted in order to some maximum order. So this merging of modes, thus forming a complex conjugate pair appears up to very high radial order of the modes. You see the almost complex conjugate symmetry here. Well, there is a dynamically unstable member of this pair. So, for instance, taking this pair here, then it merges somewhere around 150. So, and then we have a complex conjugate pair which increases its growth and damping rate once we approach L equals 0. So L equals 0 seem to be the spherically symmetric perturbations seem to be associated with the highest growth rates. Okay, well, complex conjugate symmetry contained in here. The highest unstable modes appear around here between 250 and 300. So we observe the same phenomenon here, but the phenomenon of the strange modes for Wolf-Rayet stars seems to be restricted to harmonic degrees less than 250 to 300. Well, we see some modes here seem to merge, but in between these modes which merge below some critical value of the harmonic degrees, there are modes which remain damped and which remain unpaired, and they also decrease with harmonic degree, and they form ultimately, if we go to L equals 0, they form the spectrum of normal modes. So we may consider this diagram for this diagram, which we saw for L equals 0 for the spherically symmetric perturbations of Wolf-Rayet stars as a function of mass, to be generated by merging of modes with decreasing harmonic degree, forming strange modes. These are the lines here in this diagram which no longer depend or only weakly depend on the harmonic degree, and the normal modes with a steeper dependence on harmonic degree, which then ultimately form the spectrum of normal modes, normal modes in a sense, normal compared to strange modes for the spectrum of radial perturbations. Okay, so the strange mode phenomenon as a result is not restricted to spherical geometry. It appears on all scales with harmonic degrees smaller than, say, 250 to 300. And we also have this nice complex conjugate symmetry for the strange mode. We have a pair of complex conjugate eigenfrequencies which are generated through the merging of two modes. Actually, we cannot predict which mode remains unpaired and which of these modes will pair. So this might be the subject for further investigation, for further research. Actually, in detail, we do not yet understand how these pairing and pairing occurs, and what causes the modes to pair and what causes the modes not to pair. Okay, so the result of this study then is maybe summarized. Well, to summarize, the additional modes come in almost complex conjugate pairs. The strange modes seem to be provided by pairing of normal modes and form complex conjugate pairs, and the strange modes and the instabilities are not restricted to radial perturbations, but they occur up to harmonic degree of about 250 to 300. Well, that demands, of course, a study or an interpretation, or we would like to get some deeper in understanding what causes this mode coupling, this mode merging, and why do these modes occur in complex conjugate pairs? What is the reason? That seems to be somewhat strange. And one tool to understand at least the complex conjugate symmetry in some cases is the so-called NAR approximation, which was developed in order to understand the properties of strange modes. So what does NAR means? NAR stands for non-adiabatic reversible. So what does this approximation mean, or what does this approach mean? Well, it is motivated in the first place by the observation that in these stars which are affected by strange modes, we have high luminosity to mass ratios which are reflected in a small ratio between thermal and dynamical timescale over a considerable fraction of the envelope. So that seems to be somehow related with a strange mode phenomenon. Thermal timescales are short compared to the dynamical timescales over a big range of the envelope considered. Okay, to discuss this NAR approximation, we consider the entropy. We have to do some thermodynamics. We consider the entropy as a function of pressure and temperature, so we take pressure and temperature as the thermodynamic basis. Then, as we have done often in this lecture series, we write down the differential of the entropy, and once we do it and write the entropy in terms of pressure and temperature, then we can write the differential of the entropy in terms of the relative differential of the temperature and the differential of the pressure. So ds is given by the specific heat at constant pressure times dt over T, minus nabla adiabatic times dp by dp over p. This relation has been used and derived several times in the course of this lecture. So let us ask now, how can we make ds equal to 0? Well, the change of entropy to be 0, well, an obvious way to make ds vanish, the change of the entropy vanish, is to ask or to require adiabatic changes of state. Adiabatic changes of state are characterized by the T over T being equal to nabla adiabatic over times dP over P. So the vanishing of this bracket corresponds to the adiabatic approximation, and ds can be made 0 by making this quantity or requiring this bracketed term to be 0. But there is also a second rather strange and not obvious way to get this ds equal to 0, namely by requiring that the Cp is equal to 0. So the question then is, if we can make this ds equal to 0, what does it mean if we make ds equal to 0 and the specific heat, it's not really the specific heat, it is the heat capacity at constant pressure to be 0. Actually, this approximation requiring Cp equal to 0 or the heat capacity equal to 0, that is the content of the NAR approximation. Okay, the question, of course, is it meaningful? What are the results of these approximations? And what are the physical consequences and the physical implications of such a strange way of getting rid of the derivative of the entropy or the change of the entropy? Well, the question is, where is this ds relevant in our perturbation equations? And obviously this ds or ds by dt, the change of entropy with respect to time, appears in the energy conservation equation. So to write down the energy conservation equation for radial perturbations, for instance, L dash, the derivative of the luminosity perturbation, is given by or written as I sigma. This is the remaining, or this is the remaining of the time derivative of entropy with respect to time, because this term corresponds to the time derivative of the entropy. So this is given by I sigma, denoting the time derivative, times the coefficient C1 over nabla adiabatic times the bracketed term T minus nabla adiabatic P. So we can make this time derivative of the entropy 0 either by requiring adiabatic changes of state. This corresponds to the first possibility, or we can make it 0 by requiring that this term here, that means essentially the C1 is equal to 0. The C1 contains, of course, the specific heat, and it also contains the density. So this term actually can be made 0 by requiring low density or low heat capacity. It is not the specific heat which we set to 0, but it is the heat capacity, means the heat stored per volume. This is different from the specific heat by a factor of the density. So the NAR approximation then consists of not requiring this term to be 0, but requiring this term to be 0. Well, C1, this coefficient, was found to be proportional to the ratio of thermal and dynamical timescale, and well, C1 is smaller than unity if the thermal timescale is small for a large fraction of the envelope, and that actually seems to be consistent with our findings. So the findings for this star is that the ratio of thermal to dynamical timescale seems to be small over a large fraction of the envelope. And so the NAR approximation requiring this term to vanish seems to be consistent both with our findings and the C1 being smaller than unity, being proportional to this timescale ratio, is consistent with the NAR. So what we are doing, we find that in our models, this coefficient is in fact small. This is found simply by inspection of the run of the thermal and the dynamical timescale. And what we are doing now, we put it equal to 0. Small values are approximated, small values of C1 are approximated simply by setting C1 equal to 0. Okay, the effect will be the same as the adiabatic relation. The change of the entropy with time is 0 both in the adiabatic approximation and in the NAR approximation. Another quantity is also 0 here. Once the right-hand side is 0, the left-hand side is also 0. Well, it's clear in the adiabatic approximation we have no luminosity variation, but also in the NAR approximation, the luminosity variations, the perturbations of luminosity must vanish. Okay, so to say, to compare these two approximations means, well, in the NAR approximation, ds by dt is 0 by vanishing heat capacity. C1 goes to 0, so ds by dt and ds is 0. Adiabatic means ds by dt or ds is 0 by t minus nabla adiabatic p by adiabatic changes of state, and this is enforced or given by C1 going to infinity. So we get the same result. ds is 0 once by having 0 thermal timescale and once by having infinite thermal timescale. So in both cases we are left with ds by dt, but for very different reasons. And in one case it implies a relation between pressure and temperature variation. In the other, it implies simply that this factor is 0. So what is the consequence? We've already talked about one consequence. Well, vanishing heat capacity means in principle we cannot do any thermodynamics anymore. Any thermodynamic relation, any thermodynamic statement requires a finite heat capacity. Without heat capacity, we cannot do any thermodynamics. So the question is, what are we left with? Well, the thermodynamics cannot play any role, so we seem to be left by this approximation with a mechanical system. So we only keep the mechanics of the system. Well, an argument in favor of this is the timescales which we see for the strange modes. Of course, the frequencies operate, or the frequencies are associated with the mechanical timescale anyway, but we see that even the growth rates are in the dynamical regime, that it might be an indication that because also the imaginary parts are associated with the dynamical timescale, that we are actually dealing with a mechanical system. Okay, well, next consequence has already been discussed. The luminosity perturbation has to vanish since heat cannot be stored. If we have no heat capacity, we cannot store heat. A luminosity perturbation would require heat to be stored, at least for in an intermediate, not permanently, but for certain time interval, luminosity perturbation would require a heat capacity and heat to be stored for some time. Well, another consequence is once we do not have heat capacity, this means we can also not provide, or we cannot realize heat transfers between some elements. Heat transfer, for instance, from the internal heat of the star to mechanical energy of the perturbation. That means any instability mechanism which is related or based on a thermodynamic process like a Carnot type heat engine, this cannot happen, or this cannot work. So all instability mechanisms based on a Carnot type process, they can be excluded, and that means that kappa and epsilon mechanism are excluded once we find the instabilities also within this NAR approximation. Then these cannot be caused by kappa and epsilon mechanism, because that would require thermodynamics, and this would require a finite heat capacity. So, okay. Well, and also the thermal and secular modes, which have been discussed in the beginning of strange mode research, they cannot exist because the I sigma term is now missing in our equations, and this is the only term which can be responsible for a spectrum of so-called secular and thermal modes. And finally, the last property is related to the name, non-adiabatic reversible. Well, if we now change time, or if we reverse the direction of time, that means we replace t by minus t, then the acceleration will, because of the square appearance of the time here, will not change. If we exchange t to minus t, then the acceleration will remain the same, and the only term which appears in the perturbation equation, which involves a time derivative, is the acceleration. So if this term is invariant with an exchange or with a transformation from t to minus t, or the reversal of the time direction. Well, and if you go to the perturbation equations and take, let's say you have a solution, and you take the complex conjugate of your solution and the complex conjugate of your equation, you see, because this I sigma term is now missing, then you see that with sigma also the complex conjugate of sigma should be a solution of the problem. Well, because we have only a quadratic appearance of the time here, we have only sigma squared, then with sigma also minus sigma squared. Minus sigma will be a solution. So once we have a solution, simply the symmetry of our equations guarantees that we have four solutions, namely with sigma also the complex conjugate, also the negative values minus sigma, and therefore also minus sigma, the complex conjugate of minus sigma is a solution of the problem. So the eigenfrequencies come in quartets of four solutions. In particular, once we have a solution, also its complex conjugate is a solution. This is pretty typical for mechanical system. It's no longer typical for thermodynamic system. Well, to rephrase the time reversibility, the invariance with a reversal of time, consider a solution, the time dependence of a solution, given as cosine sigma r times e to I sigma t, and reverse the time. Then the argument of cosine sigma r goes to cosine minus sigma rt, and the argument of the exponential goes with e to minus I sigma it. Once you reverse the time, well, cosine is symmetric, so cosine minus sigma r is equal to cosine sigma r, and here we have e to minus I sigma I, because once we have sigma as a solution, also its complex conjugate is a solution. That means we have also in our manifold of solutions, we have also a term which goes to e to I, from e to I plus I sigma it, we have a solution which goes to e to minus I sigma I. So time reversibility is somehow connected, or time reversibility means that sigma and sigma and its complex conjugate is a solution, Or on the other hand, if sigma and its complex conjugate is a solution simultaneously, then this indicates that the system is time reversible. That's why this approximation is called non-adiabatic reversible approximation. And well, this time reversibility and the appearance of eigenvalues in complex conjugate pairs is typical for mechanical system. It's untypical for, it's not typical for thermodynamic systems. Okay, now we have considered this approximation, and of course we would like to know, at least for the Wolf-Rayet stars, what is the result if we perform, instead of the full non-adiabatic analysis, we perform an analysis where we artificially put the I sigma term equal to 0. That means in the energy conservation equation we artificially put this term to 0. So what is the result? We perform now an analysis exactly the same way, but without this I sigma term. This is then the NAR approximation for our star. Let's compare the result for the helium 0H main sequence models for spherically symmetric perturbations. Now this is the full result. This is the complete result, and the diagram on the bottom is the NAR result. You have to look very carefully to see any difference. Well, what seems to be lifted, or what seems to be done here, well, the thick dots denote an unstable mode, because in the NAR approximation, it means that we have always complex conjugate pairs. So each of these thick dots denotes both an unstable and its complex conjugate part. So these are, on these thick dots, we have two modes: one stable, one damped mode, and its unstable counterpart. So, and here we have a small difference in frequency between the unstable and the stable counterparts of these almost complex conjugate pairs. So this means it gets exactly now the same frequency. The ordinary modes, the normal modes, are seem to be not affected by this approximation, and even the strange modes are not affected very much by this approximation. So for Wolf-Rayet stars, we deduce from this experiment that the NAR approximation for Wolf-Rayet stars is even quantitatively not bad. Let's compare the imaginary parts in the upper diagram. Well, these are the damping rates of the normal modes. Well, we expect them to collapse to 0, because if they wouldn't collapse to 0, they would have to produce a complex conjugate pair instead. But all these normal modes, in fact, they collapse to 0 imaginary part, and now this pair of complex conjugate modes becomes exactly complex conjugate, whereas in the full problem it's only approximately complex conjugate, and we are left with much nicer diagram. All modes all ordinary modes have 0 damping rates, and the complex conjugate pairs are pretty similar to the unrestricted, not approximated full non-adiabatic problem. So this approximation, even if it sounds a little bit strange, putting the heat capacity equal to 0, it provides, concerning the stability analysis, even in the quantitative sense, it provides very good approximation. Okay? So it doesn't seem to be that bad to adopt this approximation. So we are left with the following result. For Wolf-Rayet stars, the NAR approximation gives even quantitatively satisfactory results. Well, we can do the same for the hydrogen-deficient carbon star models. Well, if we do also the NAR approximation, well, we again see this trace of mode 1. The mode 1 is still there. Also, the mode 5 is there with an extremely high growth rate. But now we see some staircase behavior for the high frequency modes in the NAR approximations, and it's a pity that you don't see what happens here, but it looks a little bit different from just a mode passing through the other sets of ordinary modes. Once we have a crossing of these modes, then they seem to have appeared in the following way, or they seem to form in the following way. So these are two crossing modes, and once we look for the imaginary part, it forms such bubbles. So it seems that the full non-adiabatic problem of the extreme hydrogen deficient star is some phenomenon which passes here, which forms very strange coupling or merging and demerging of modes, which is associated with bubbles of complex conjugate pairs. And these bubbles, once we somehow smear out these bubbles, then we arrive at the full non-adiabatic problem. So keep this in mind, and if you smear out these instabilities or the negative values of the growth rates here and compare it to the full problem, let's go back to the extreme hydrogen deficient carbon stars. Let's look for the modal diagram. Well, these are the imaginary parts. So you see these maxima seem to be reminiscent of these bubbles which are now merged or smeared out, whereas in the real part you still see the trace or some trace of this mode running through. In the NAR approximation, it looks a little bit different, but at least the trace of this mode is also seen in the NAR approximation, and moreover, the value of the value of sigma I is comparable. This value found in the full problem is comparable to the value of the instability or the growth rates in the NAR approximation. So the NAR approximation at least provides some approximation also to the unstable mode. And that, of course, we are mainly interested in the unstable modes and possibly in the instability mechanism which is behind these modes. Okay, also in the case of the hydrogen deficient carbon stars, this approximation seems to provide an approximation which is even quantitatively not too bad. Okay, so well, all these phenomena, all what we have talked about now, is or seems to be associated with the crossing of modes. If we go to the Wolf-Rayet stars, well, we see that the strange modes are either formed by merging of modes, so to say, by coupling of modes, and then subsequently by the crossings of two sets of modes. So the coupling or the crossing or the interference or the resonance of modes seems to be, in this phenomenon, seems to play a basic role. And this might be the motivation to study or to deal with mode coupling in detail. And that's what we want to do now. So we consider the coupling or the resonance or the interference of two sets or of two modes. So the observed crossing of modes will gives rise to an investigation of mode coupling. So consider two configurations or two sets of modes which interact with each other. So we have considered two systems or two subsystems which formally might be described by two independent dispersion relations. So you have one set of modes, which is one set of modes, for instance, which depend on a parameter. So you have sigma r as a function of parameter. Let the parameter, for instance, be the mass. Then we have a set of modes which have almost no dependence on the parameter m. This is one set of modes. Let's call, or let them be described by a dispersion relation d1 of omega equal to 0. So this is the set 1 described by a dispersion relation d1 of omega. Then let's consider a second set of modes. This is set 2, and the set 2 should be described by an independent dispersion relation d1 of omega equal to 0. Well, the first dispersion relation will have solutions omega 1, and the second set will have solutions omega 2. So these here are the omega 1s, and these here are the omega 2s. Well, and we have crossings between these two sets of modes, and the crossing, if they are independent, of course, then these two dispersion relations have to be satisfied separately. Now, if we admit some coupling between these two sets of modes, then we can describe the coupling simply by the product of these two dispersion relations not being 0, but being equal to some coupling functions epsilon of omega. Epsilon may depend on omega itself, and epsilon should describe possibly a small coupling between these two sets of modes. So if epsilon is 0, then we arrive for the solution of the system. If no coupling exists, we have d1 of omega equals 0 and d2 of omega equals 0 as the separate dispersion relations. Now, if epsilon is not 0 and we have a small coupling, well, if d2 is not 0, then we can write d1 of omega is epsilon over d2, and once d2 is not 0, then this will be small, and d1 of omega equal to 0 will be the solution of the problem. Once the same is true for d2, if d1 is not 0, then d2 equal to 0 will be a solution of for determining the eigenfrequencies omega 1 and omega 2. This happens that omega d2 is not 0 and d1 is 0. D1 equals 0 gives the dispersion relation or determines the roots of this equation. Is required is that these two d1 and d2 are not 0 at the same time. So the requirement is that d1 and d2 are not 0 at the same time. This means that they have a common root or that the modes cross. So apart from the mode crossings, these are these points here, we have the original dispersion relations, we have the unperturbed or the uncoupled dispersion relations, and we have the uncoupled modes only close to these crossings we have to take into account the coupling of the two dispersion relations described by epsilon of omega. Okay, so apart from the crossings, we have the original modes, but close to the crossings, we have to take into account the coupling between the two sets of dispersion, sets of modes described by the dispersion relation D1 and D2. So if D1 and D2 are simultaneously zero, that means if omega 2 is equal to omega 1 is equal to omega 2, that means at a mode crossing, we have to consider what happens due to the coupling. Now we describe the difference of the original frequencies omega 1 and omega 2 by small delta, and we describe the difference of the final frequency omega with compared to omega 1 with capital delta. According to these definitions, we may write omega as omega 1 plus delta, which is expressed in terms of omega 2 equal to omega 2 plus, because omega 1 is delta plus omega 2, so this is omega 2 plus small delta plus capital delta. And we have to solve the dispersion relation D1 at omega might be expressed in terms of omega 1 plus capital delta times D2, which of omega, which might be expressed as omega 2 plus delta, small delta plus capital delta equal to epsilon. Okay, what we are doing is we expand these dispersion relations around omega 1 and around omega 2. Then we have that this dispersion relation or this function in an expansion may be expressed by d1 at the point omega 1 plus the derivative of d1 with respect to omega times delta, and the similar process here for the dispersion relation d2 is d2 of omega 2 plus delta times the derivative of dispersion relation 2 with respect to omega is equal to epsilon. Now d1 of omega 1 and d2 of omega 2 is 0 simultaneously because we are expanding around a crossing of two modes. Then we are left with a quadratic equation for delta, measuring the difference between the final value of the frequency and omega 1. Delta times delta plus small delta plus capital delta is equal to epsilon divided by the derivatives of the original dispersion relations d1 and d2 with respect to omega. Well, this is a quadratic equation, and we can easily solve this quadratic equation. Solution of the quadratic equation gives capital delta is minus 1/2 the difference of the original uncoupled eigenfrequencies plus the square root of delta squared plus epsilon divided by the derivatives of the dispersion relations. If delta is large, if the difference of omega 1 and omega 2 is large, that means we are far away from the crossings, delta large, then we can neglect this term compared to delta squared. So we are far off the crossing. Omega 1 delta is omega 1 minus omega 2, and this means omega 1 delta big means we are far away from the crossing. Then we can neglect this coupling term, and delta is either 0 or minus delta, and this means, according to the definition, that delta is omega minus omega 1. We have omega equal to omega 1 and omega 2. So we arrive at the decoupled value. What happens at the crossing if delta is small, or delta might be neglected with respect to this epsilon term? then we have omega delta is omega 1 minus omega 2. So omega is omega 1 plus minus, taking the definition of capital delta, plus minus the square root of this coupling term, which is given in terms of epsilon, the coupling between the two dispersion relations divided by the derivatives of the dispersion relations. Okay? Now let's assume for simplicity that omega 1 and omega 2 are real frequencies. How does this look like? Okay, if d1 by the omega and d2 by the omega are real, omega 1 and omega 2 are real, and epsilon is a real quantity, well, then in the case that the term underneath the root is positive, we arrive at the following coupling picture. The dashed lines are the omega 1 and omega 2, which cross at or which are in resonance at some position, depending on the parameter. So what we get in this case, when this term is positive and the root here is real, then we get the following picture. Omega 1 is now, or the previous omega 1 is now connected continuously to omega 2, and omega 2 is now connected continuously to omega 1. This is called the coupling according to the avoided crossing scheme, because the crossing is avoided and then the frequencies avoid each other simply by connecting omega 2 to omega 1 and omega 1 to omega 2 and vice versa. Okay, now let's consider that the term underneath the root here, the argument of the root is negative. Then this, of course, this provides a complex conjugate pair of solutions. So how are the functions connected now? These are the original uncoupled values omega 2 and omega 1. Now they couple in a way, it's just the properties of this root. They have a common, they are now connected. Omega 1 again connects to omega 2, and omega 2 connects to omega 1. And once at the point of where this relation gets a vertical tangent, these modes seem to merge in that sense, and they have a common real part. This is when this root comes into play. There is one common real part, but two complex conjugate imaginary parts. And once we plot the imaginary part here, then we have a bubble or an instability band or a bubble of instability between those places where these modes have merged to give a complex conjugate pair. Okay? It's simply discussing the properties of this quadratic equation. So we have in principle two ways how modes can couple, or two ways in which a mode crossing may unfold. It's either the avoided crossing scheme or it is the instability band scheme. Now let's go back to our extreme hydrogen deficient carbon stars. Well, these guys remind you of bubbles of instability, and here, these guys over there, they remind you of avoided crossings. And if the picture of if the graph would have higher quality, you would also see that you find exactly the coupling scheme which we have described in the last picture. So what you see here, I will draw it here on the blackboard shortly. So we have a set of normal modes which are crossed by an additional mode. This is the uncoupled system. Now, in the upper part, it seems that we have coupling according to the avoided crossing schemes. In other words, the coupling constant here, the coupling epsilon is positive. So we connect it in that way. So this is connected to this way, in that way, and here we have connection according to that way. This is an avoided crossing. Here, let's do another avoided crossing. So they are connected that way, and these are connected this way. So this gives this staircase impression, and these are the modes seen here. So this is the trace of an additional mode which has passed through the set of normal modes. Now let's change the coupling scheme. Let's change it to instability bands. Then it will have to be connected that way, this way here, and we have a common real part here. The next one also giving this coupling scheme. Then we have that way, and we have a sequence of instability bands or instability bubbles. And in the imaginary part, we have a complex conjugate bubble here. And well, let's do it. This is a complex conjugate bubble here, and a complex conjugate bubble here. So using that coupling scheme, or having in mind the coupling scheme which we have discussed in the last few minutes, we can now explain or interpret this diagram simply by one mode crossing these the normal modes and coupling either according to the avoided crossing scheme or according to the instability band scheme. So the consideration of the general possibilities of mode coupling helps in some sense to interpret this diagram and to understand at least partially this diagram. So it's a tool for getting some order in modal diagrams and to interpret them in terms of crossings of different kinds. Okay, because this is a little bit counterintuitive, let's give some examples for mode coupling, which you probably already know, but you are probably not aware of the fact that mode coupling is present in these cases. Well, first case is the so-called double pendulum. The double pendulum consisting of two pendula acting under the action of gravity and a coupling spring which have different length. Okay, this is the situation. We have two pendula which have different length, one with the length L and the other one the length capital L, two masses, and which are coupled through a spring with constant D and gravity acting in the vertical direction. You probably know this problem from basic physics. Well, how many modes does this system have? We have two systems, and obviously we are talking about mode coupling. So how many modes does this system have? Infinitely many. Well, two pendula, two modes. So, and we are considering now a system with two modes and the crossing of these two modes, which can be done completely in an analytical way. Okay, so let's consider the equations of motion for this pendulum. Well, you probably should be familiar with that. Well, the forces which act on the pendula are either gravity and the spring. The force exerted by the spring. Well, the gravity, so to say, the horizontal component of the gravity is gravitational force is mass times the gravitational acceleration, and the component in the direction of x, this is the motion of our in a certain approximation, the motion along which our pendulum move. So x1 will be the displacement of pendulum 1, and x2 is the displacement of pendulum 2. So we are left with that the gravity is, the horizontal component of gravity is x1 over the length, and for the pendulum 2 it's x2 over capital L. This is the component of the gravity parallel in the horizontal direction or parallel to the displacement of the pendulum. The spring is the force exerted by the spring is spring constant times the difference of the displacements of x1 and x2. Well, a corresponding formula for the gravity and the spring of pendulum 2. The force exerted by the spring is just the opposite, because actio equal to reactio, it has to point in the opposite direction. The gravity is analogous to the gravity of the first pendulum. So these are the forces acting on our pendula, and according to that we have the equation of motion. Mass times acceleration of pendulum 1 is given by gravitational force in the horizontal direction acting on pendulum x1 plus the force exerted by the spring. The opposite sign here for the second pendulum. Now, rearranging these two equations of motions, we are left with a system of two differential equations with respect to time, where we have x, the acceleration given by the gravitational forces, and the spring forces. Now, this is an equation, a linear equation with constant coefficients. Linear equation with constant coefficient have as a solution exponential of time. This time derivative will give a minus omega squared instead of the second time derivatives here. And we are then left with two equations for x1 and x2, the displacements x1 and x2 for the two pendula. Well, this is a homogeneous linear system with respect to the displacement x1 and x2, and might be written matrix as a matrix times the vector x1, x2, and this has a solution only once the determinant of A is 0. So the condition for the solvability of the system is minus omega squared plus g over L, this is the first bracket, times the second bracket, minus the diagonal terms minus d over m squared is 0. Or we rearrange it in the following way: omega squared minus omega 1 squared times omega squared minus omega 2 squared is equal to d over m squared, which we identified with the coupling of the two systems epsilon, which is in this case bigger than 0. So omega 1 squared is simply an abbreviation for g over L plus d over m. This is the first, so this might be denoted by omega 1 squared, and we have omega 2 squared as an abbreviation for this term. So if epsilon is small, or the coupling is small, or in other words, the spring is weak, then we have two independent frequencies, omega 1 and omega 2, determined by the vanishing of the first bracket and the second bracket, respectively. We can also write down an exact solution, because this is a quadratic equation for the omega squareds, and we can write down the exact solution in that case. So the exact solution is given by this, the solution of the quadratic equations. So once the difference of the unperturbed or the uncoupled frequencies is big, that means this term is bigger than epsilon, then we get as a solution of the full problem, as an exact solution, omega 1 squared and omega 2 squared. This is no longer true if epsilon is no longer small compared to the difference of the uncoupled frequencies. In that case, we get omega squared is the mean, or is the average of omega 1 squared and omega 2 squared plus minus square root of epsilon, and epsilon was simply the square d over m squared. So this is given then omega squared is the mean of these two plus minus d over m. Once we apply the mode coupling formalism to this system, we arrive at d1 of omega squared times d2 of omega squared is equal to epsilon. The d1 is omega squared minus omega 1 squared, and this similar relation for d2. The epsilon is d over m squared. So we have two dispersion relations, and we have a coupling between these two, and we can apply the coupling formalism. Then the d1 over d2, the d1 over d omega squared, which is required for the coupling mechanism, is 1, and similar d2 by the omega squared is 1, and we get, if delta is large, if the difference of the omega 1 and omega 2 is big, then we get as the capital delta 0 and minus delta, and we get the decoupled values, meaning omega squared is omega 1 squared and omega 2 squared. If delta is small, then the coupling epsilon is significant, and we are left with omega squared equal omega squared is omega 1 squared plus the root describing the coupling. This is omega 1 squared plus minus square root of epsilon, and this is omega 1 squared plus minus d over m. Okay, and if you compare it with the exact result, well, then it is the mean of omega 1 and omega 2. If we are at a position where omega 1 is equal to omega 2, this is omega 1 squared plus minus d over m. So it's exactly the same result. So what does it mean if we try to illustrate this in a graphic way? So let's write down, or let's illustrate this behavior of these two modes. We have two modes corresponding to the two pendula. Then omega will be a function of the length L, small l, whereas we take, in our experiment, we take the length of one of these pendula equal to constant. So we take the pendulum 2 with length capital L, we take this constant, and we will have omega 2 constant as a function of the length of the pendulum 1, which changes according which is in the experiment taken to change. So omega 1 goes essentially like 1 over L plus some correction due to the spring constant. And what happens now, and this can be explicitly seen either in the exact solution or in the coupling formalism. Now the omega 1 is now connected continuously to omega 2, and omega 2 is connected continuously to the omega 1. And the separation of these two frequencies is exactly delta and controlled by the coupling or by the spring constant. If we artificially would have the case, which is not exactly the case here for the double pendulum, that epsilon is smaller than 0, if, for instance, the spring constant would be imaginary, what that means is not clear. So if artificially epsilon would be smaller than 0, then they would couple in the way that here we have a common real part. Again, omega 2 is connected to omega 1, and omega 2 is connected to omega 1 here. We have a common real part, but we have a bubble of instability around the coupling of these two modes. So this would be the case if we artificially switch to a negative value of the coupling. So we have an avoided crossing. The avoided crossing is realized in this system of the covered pendulum. Probably you have never come across the fact that your double pendulum, which you consider in lab courses or so, that this involves the coupling scheme of two modes according to avoided crossing. And if you artificially change to epsilon smaller than 0, you could even produce, in this simple system, could even produce an unstable situation where you produce an instability bubble by the coupling of two modes realized here with the double pendulum. Okay, this afternoon I think we have run out of time. This afternoon we will consider another problem, which then brings us back to astrophysics and how a simple system which by which we can intuitively interpret the modal diagrams of a star and understand what's going on there. Okay, thanks very much for this morning, and we will continue at this point in the afternoon.